Hi, welcome to week 4 of Understanding Quantum Computers. We hope you're enjoying the course so far. This is going to be our last individual video for coming along as sort of your support videos. And today I'm doing it just by myself. Sato's off somewhere doing some actual work somewhere. So today I want to talk about a few different things. First off, most important, there were some questions about NV diamond on the course. So let's talk about that a little bit. You might remember this. We talked about this early in the course. We used it as, we described it as the structure of crystalline silicon. And we talked about the fact that we're getting down to small sizes in individual transistors relative to the size of the silicon crystal. And so that was one of our motivations for wanting to build quantum computers. Well, as it turns out, this model, this structure for the crystal is the same for diamond as it is for crystalline silicon. So of course, each of these individual atoms are carbon instead of silicon in diamond, but it's the same structure. So we can use this as a model for diamond. Now, NV diamond is nitrogen vacancy diamond. So let's see. Let's take, for example, on this corner here. Nitrogen vacancy, what that means is that we take out one of the atoms and replace it with a nitrogen atom instead of a carbon atom. So for example, let's see, where's a good place to do this? I guess right here. So if we took out this individual atom here, right here, that my fingers are wrapped around, you can see that it's bonded to 4 other carbon atoms. 1, 2, 3, 4. So it's got 4 bonds for it. But nitrogen prefers to have 3 bonds instead of 4. So if we take out this particular atom here, we can and replace it with a nitrogen atom, then it will couple well to 3 of these atoms, but the 4th one will be left sort of hanging. And that creates what's called a nitrogen vacancy inside the overall structure. We wind up with nobody to bond it to. This is a figure from Wikipedia. You can see here what happens is we wind up having a nitrogen atom in one particular place inside the structure instead of the carbon atom. And you can see that it's coupled to 3 atoms instead. And there's a missing carbon atom there. So what happens here is that the bonds from the other carbon atoms wind up leaving a hole there, or a gap there. That's called the vacancy itself. And what happens is that because of the arrangement of those electrons, it winds up attracting another individual electron which is kept trapped in that particular spot, and that atom, or that electron doesn't move. It stays right there in this particular place. So then we can control that individual electron and use the state of that individual electron as our qubit. That's our primary qubit in an NV diamond system. Now, as it happens, also, if these other white circles represent carbon atoms, some of these have a nuclear spin instead of having no nuclear spin. So there are different isotopes of carbon. When the nucleus has a spin, as in carbon-13, then we can use that nuclear spin also as a qubit. And so what we do is we wind up transferring the state of our qubit from the vacancy into the nuclear spin of one of the nearby atoms. And so then we actually have 2 qubits that are available inside this. One that's very active and that we can use to interact with light, and one that's not so active and that's pretty well shielded and has a long lifetime and we can use for longer qubits, longer lifetime qubits, and keep it around, which is very useful, for example, in quantum networking. Hope that answers your questions about the NV diamond. I think that pretty much covers it. One of the other questions that came up this week is confirming the distinction between physical qubits and logical qubits in error-corrected systems. With error correction, we take one logical qubit and encode it into the state of multiple physical qubits. And so the number of physical qubits we actually need is that expansion factor times the number of logical qubits we want to have in the system. So if our quantum algorithm uses 50 logical qubits, and each logical qubit requires us to have 1,000 physical qubits, then we would need 50,000 physical qubits to to have a functional quantum computer with full quantum error correction. That's maybe about where we are with respect to some error correcting codes. Of course, we would rather have that factor be much smaller than a factor of 1,000. And in fact, it might be as low as, a factor of 10 to 20 for different kinds of codes. But for the surface code that we think is the most viable one for actually implementing, the factor of the expansion factor is actually going to be quite a bit larger. It could be high tens to low hundreds up to as high as 1,000. So yes, the size of the physical machine and the number of physical qubits we have to control grows rather large rather quickly. As we're coming down to the end of the course, a number of you are probably looking ahead at the further study step in the course, or you're wondering what to do next, what to study next. There's a great list of resources in that step, and we cover places to find good books and introductory articles and topics that go into more depth. There are also an increasing number of online courses like ours, and those tend to start at a little bit higher level of mathematical sophistication. So finishing off this course and then going into one of those other courses actually makes for a pretty good sequence. Besides the ones that are actually listed on the step here on FutureLearn, there's also a recent course introduced by Stephanie Wehner from the Technical University of Delft and her team on quantum networking. She's one of the world's leading experts in quantum internet and quantum networking, which is also the area where we do actually a lot of our own research. I actually haven't gone through the course yet, so I can't tell you much about the content, but knowing the people who put it together, I'm sure it's a fantastic course. And hopefully that will make a good follow-on to what we're doing here in this course as well. So good luck with those reading materials. We think they'll be a great follow-on for going deeper into this, and hopefully the intuition that has built from working on this will help you out with that. Finally, I really have to go back and thank again everybody who's participated in the creation of this course, the online course that you're taking here, from Professor Keiko Okawa to Yasui-san and Matsuzawa-san, who did the videos for the earlier course, and Nibe-san, who was deeply involved in that, and of course Sato-san, who was my co-teacher in all of this, and the students, Takaaki and Shin and several of the others who participated in both the creation of the videos and especially in mentoring the people online, providing feedback to that. And of course, Arima-san, who's making these videos, these helpful videos for you all. Thank you all for everything you've done for this, and especially to the teams that have been involved in translating the course into Japanese and now into Thai. I really think that's making this a much more accessible and global resource for everybody to use. And then, of course, finally, thanks to all of you all who are participating in the course itself. There's no point in us doing it without you, the learners, and we're really happy with the number of people who've been involved in this and how interactive everyone has been and how far you've come with the learning. We're really impressed, and we hope you'll keep learning about quantum computing, which we think is the most exciting and potentially highest impact field today in the larger area of information technology, and it's one of the most important things going. So, see you online. Hope to see some of you at quantum computing conferences or as quantum computing graduate students or even as undergraduates here in my course later on. Thanks and bye-bye.